Hello everyone, welcome to Analog Communication Tutorials. In this video, I am going to derive expressions for time domain representation of frequency modulated and phase modulated signals. Please note, in my previous video, I have given a brief introduction to angle modulation. That video will be a prerequisite for this one. You can watch that video by clicking on the link shown in the top right corner right now, or I will leave the link of the same in the video description below. Let us start our discussion by considering theta I of t as the angle of modulated sinusoidal carrier at some time t. Also, theta I of t is assumed to be a function of the information bearing signal or message signal, which is generally represented by m of t. Therefore, the resulting angle modulated wave can be given by the expression S of t equals AC into cos of theta I of t, where AC is the carrier amplitude and theta I of t, as previously said in the first point here, is the angle of the modulated sinusoidal carrier. Let me first derive the expression for the time domain representation of phase modulation first. What is phase modulation? Phase modulation is that form of angle modulation in which the instantaneous angle theta I of t is varied linearly with the message signal, which is generally represented by m of t. And the expression for instantaneous angle theta I of t is given by 2 pi fct plus kp into m of t, where 2 pi fct represents the angle of the unmodulated carrier and kp is the phase sensitivity constant of the modulator, and it is measured in radians per volt. Let us now substitute equation 3, which is theta I of t, into equation 2, which is the angle modulated wave, to obtain the time domain representation for the phase modulated signal, which is given by AC into cos of theta I of t, and this complete term is taken from equation 3. Please note, equation 4 represents the time domain representation of phase modulated signal. Further, the instantaneous angular frequency, which is represented by Fi, can be given as Fi of t equals d by dt of theta I of t. I have previously derived this expression in my previous video. I would once again recommend you to watch that video. Let us now substitute for theta I of t from equation 3. So, Fi of t equals d by dt of 2 pi fct plus kp into m of t. Now, coming to the first term, d by dt of 2 pi fct will result in 2 pi fc, and d by dt of kp into m of t will result in kp into d by dt of m of t. This equation represents the instantaneous angular frequency Fi of t for the phase modulated signal. What is to be noted from this equation is that in phase modulation, the instantaneous frequency Fi of t varies linearly with the derivative of the message signal m of t. That is, Fi of t varies with respect to d by dt of m of t. Let us now move on and find the time domain representation for frequency modulated signal. Let us first define frequency modulation. Frequency modulation is that form of angle modulation in which the instantaneous frequency Fi of t is varied linearly with the message signal m of t, and this variation can be represented by Fi of t equals Fc plus Kf into m of t, where Fc is the frequency of the unmodulated carrier and Kf is the sensitivity constant of the modulator, once again measured in hertz per volt. Let us now recall the relationship between the instantaneous frequency Fi of t and the angle of the unmodulated carrier theta I of t. Please note, this is supposed to be theta I of t. There is a correction required here. The relation says Fi of t equals 1 by 2 pi d by dt of theta I of t. Let me now take the 2 pi to the LHS. So, the LHS becomes 2 pi into Fi of t equals d by dt of theta I of t. Now, interchanging LHS and RHS, I will find d by dt of theta I of t equals 2 pi into Fi of t. Let us now take integration on both sides. So, d by dt of theta I of t becomes theta I of t, and in the RHS we introduce the integral term integral 0 to t 2 pi Fi of t into dt. Please note, we have previously obtained the expression for Fi of t, and this is equal to Fc plus Kf into m of t. Now, I will substitute for Fi of t in this place of the equation, which is shown here. So, theta I of t equals integral 0 to t 2 pi into this complete part is theta I of t. Let us now split the part. So, the first term will be 2 pi Fc into integral 0 to t dt, and the second term would be 2 pi Kf into integral 0 to t m of t into dt. Coming to the first term here, integration 0 to t dt is equal to t. So, the first term reduces to 2 pi Fc into t. Coming to the second term, there is no change. We have retained the same as it is, which is 2 pi Kf integral 0 to t m of t into dt. Let us now recall the expression for the angle modulated signal, which is given by S of t equals AC into cos of theta I of t. So, I will now substitute equation 8, which is for theta I of t, in this part of the equation to obtain the time domain representation for the frequency modulated signal, which is given by S of t equals AC cos 2 pi Fct plus 2 pi Kf integral 0 to t m of t dt. Equation 9 represents the time domain representation for the frequency modulated signal. To summarize, in this video we have obtained the time domain representations for the phase modulated signal S of t, which is given by AC into cos 2 pi Fct plus Kp into m of t, and the time domain representation for the frequency modulated signal, which is given by AC cos 2 pi Fct plus 2 pi into Kf integral 0 to t m of t dt. Having now found the expressions for the time domain representations of both phase as well as frequency modulated signals, let us now compare and contrast and find some important observations. The first important observation that is made by comparing these two equations is that both Fm and Pm are not only similar, but they are almost inseparable. That is, replacing m of t for equation in phase modulated signal with integral m of t, we obtain the equation for Fm. Therefore, we can say that a signal which is frequency modulated wave corresponding to m of t is also the phase modulated wave corresponding to integral m of t. In a very similar fashion, we can also say that a phase modulated wave that corresponds to m of t is the frequency modulated wave corresponding to d by dt of m of t. So, we can finally state that in both phase modulation as well as in frequency modulation, the angle of the carrier signal, which is represented by theta I of t, is varied in accordance with some measure of the modulating signal m of t. In phase modulation, the instantaneous angle theta I of t is directly proportional to the modulating signal m of t, whereas in frequency modulation, theta I of t is proportional to integral of m of t. Well, that is about the derivation for the time domain representations of phase modulated and frequency modulated signals. In my next video, I will be discussing on single tone frequency modulation. So, stay tuned. With that, we come to the end of this video. on the time domain representation of PM and FM waves. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on analog communication. Thank you for watching. Have a good day.